Maximum likelihood estimation. As a machine learning student, in many places you would have heard this term maximum likelihood estimation. Maybe your professor would have written some log likelihood and then took the maximum likelihood estimation. If you have ever wondered why is this maximum likelihood estimation so important and what exactly is this, then this lecture is for you. We are going to clarify what exactly is maximum likelihood estimation, how to find it out, and what is the significance of finding this maximum likelihood estimation in a machine learning model, right? So the first thing you want to understand is MLE, maximum likelihood estimation. This is a statistical method for estimating the parameters of a probability distribution. Generally what happens is, let us say you are building some machine learning model, a classification model or something. Many times you will be building a probability distribution. So MLE is a method for identifying the parameters theta of that probability distribution by choosing values that maximize the likelihood function. This is the point. So what do you generally do in a model? For a model, let us say you have some model M, you will be given the data. Data X will be given. Then you want to train this model using data X. You want to train the model such that the probability of this particular X is increased. That is, this model should be providing you further responses which are similar to the training data. That is, whatever it learned from the training data, it should be able to understand everything. And then when you give any new data, depending on whatever it learned previously from the training data, it should be able to output the right outputs. For this, what should it do? The probability of observing the given data, that should be maximized. Whatever is the given data, probability of observing that if you go through the model should be maximized. In order to achieve this particular thing, you use maximum likelihood estimate. You are trying to identify see what is parameter here. These are the model parameters. What are you training the model for? Whenever you are training a model, what are you doing? You are training parameters of the model. You will alter the parameters such that there will be one sweet spot. At one sweet spot, your parameters will be tuned such that for your data, you will always get the perfect output. In machine learning, when you say perfect output, it is not like you will get one particular answer, but the best possible answer in this scenario. That is what you will get. Okay. So theta, which are the parameters of the model, that is what you want to find out. You want to find out the right parameters. Once you find out the right parameters, your model is trained. What is training? Training is identifying parameters. This is what you call as training a machine learning model. Maximum likelihood estimate, this will help you identify the right parameter, that is in training the model. Now let us say, how is this done? What exactly is the use of it? In the previous lecture, we already learned about likelihood. So likelihood, I'm going to directly write here. If you are having, let us say, some experiments, x1, x2, not experiments, observations up to xn, then if the probability density function is f of x theta, then what did we learn in the last lecture? Likelihood L theta, this can be written as pi, that is product of I is equal to 1 to n f of x theta. This is the likelihood. Now, what is maximum likelihood estimation? MLE. What is maximum likelihood estimation going to do? It is going to find out that particular value of theta. I'll call it as theta cap. This theta cap is your maximum likelihood estimate. This particular theta cap is the parameter value that maximizes L theta, that whatever is your likelihood, that is maximized by this particular value of theta. That means whenever you use this particular value theta cap, your likelihood L theta will take its maximum value. MLE picks the parameter estimates that makes the observed data most probable. This is what we learned in the last lecture about likelihood. Your data is already observed, then you have to pick the value of theta using MLE. So in likelihood, theta is a variable. In MLE, maximum likelihood estimate, from those variable values of theta, you want to find that particular value called theta cap, which will maximize your likelihood. Another way of seeing this is, let us say you just wrote down the probability of your data as a function of unknown parameter theta. There is unknown parameter theta. If you write down probability as a function of your unknown parameter theta, then if you simply pick that particular value of theta cap that maximizes this probability, then that is called as maximum likelihood estimate. Okay, so this is the concept. Next, what we are going to do, we'll do two things. One, we'll explain how exactly maximum likelihood estimate should be found out, what is the procedure, and then we'll take one example. We'll take a very basic example. We'll derive the maximum likelihood estimate in that example. That will make the process of derivation easier for you, clear for you. Most important thing that I want is the concept of maximum likelihood estimate. This should be crystal clear for you. That will also happen once we complete the experiment. First, we'll see the process, how to find out maximum likelihood estimate. Then we'll see through an example, how can you actually do it. So first of all, your maximum likelihood estimate. What are you going to do for this? You know, you have the likelihood L theta. This is product of I is equal to 1 to n. What are the values? F of xi theta. This is what is your likelihood. In the last lecture, we already discussed that whenever you want to do these calculations, what do you do first? You take log of likelihood. So your log likelihood, I'll put small l. This will be log of L theta. Then what will this become? This product will become sum. So it will be sigma I is equal to 1 to n log of f of xi theta. So this we already discussed in the last lecture. Why are we taking this log? Because taking the log converts product into sum, and when it is converted into sum, numerical stability increases, right? So in practice, understand that in practice, even though ideally you want to maximize likelihood, in practice, what you do is you always maximize log likelihood, because whether you maximize likelihood or you maximize log likelihood, you're going to reach the same answer. But maximizing log likelihood, this is much easier and it is numerically more stable. That is why you are going to maximize log likelihood. Then what will you do? You want to solve for del by del theta of L theta, and this you want to equate to 0. After this, when you equate to 0 and you solve it for the value of theta, one more thing is you have to see the second derivative, or you call it as Hessian. You have to see that it is a negative definite. It should be a negative definite. Why should it be a negative definite? The reason is at that solution you want a local maxima, so that it will be maximum likelihood estimate. For it to be MLE, you have to make sure it is a local maxima. For that, you have to confirm that second derivative or Hessian is negative definite. And then if you solve for the first derivative, if you equate to 0 and solve, you will get that particular value of theta, which is maximum likelihood estimate. We'll just write down steps one by one so that later if you want to solve, you'll be very clear. What is step number 1? How to find MLE. Okay, this is what we are discussing. For this, step number 1 is you have to write down likelihood L theta, or ideally you should write down log likelihood. This is what is more numerically stable. So even though you want actually likelihood, you are going to use log likelihood. What is the second step? In the second step, you want to differentiate L theta. Here we'll take log likelihood. Small l I'm using in order to show that it is log likelihood. Okay. Differentiate L theta with respect to theta. That is del by del theta of L theta. This is what you're going to do. After this, what should you do? You should solve del L by del theta. You equate to 0 and you solve this for the value of theta. You found out the log likelihood, then you differentiate it with respect to theta, then you equate it to 0 and you solve it for the value of theta. And one more thing is you want to check the second derivative or Hessian. Why should you check the Hessian? It should be a negative definite at the solution. That confirms you have a maximum, right? This is why you should find Hessian. And one more thing, I'll write it as the fifth point, that an analytical solution may always not be possible. In the example that we are going to take now, we'll simply get an analytical solution. But sometimes this direct analytical solution, this won't be possible. Then what will you do? You will use numerical optimization. That is when you come into those techniques that you heard, like gradient descent or maybe EM models. All these things comes in as numerical optimization techniques. Then you have Newton-Raphson, you have Fisher scoring. All these are different methods for numerical optimization. That we'll discuss when we reach the numerical optimization lectures. There we'll actually discuss what exactly these things are, how to do those numerical optimizations and those things. For now, just understand that this is the process. If you can get an analytical solution, well and good. Otherwise, you may have to look for numerical optimization methods. Next thing we are going to do is, we'll take an example. We'll find out the maximum likelihood estimate. Most important thing that I want from this is, I want you to understand what is the logic of finding maximum likelihood estimate. You understood the theory here, but when you actually see the value, you will understand, okay, this is the value I was looking for. So that is what I want you to understand. Let us move into an example. We'll take the simplest possible example. So the simplest example is coin toss experiment. The reason I'm taking coin toss again is, in the last lecture where we discussed about likelihood, we already discussed coin toss experiment, which means the steps till finding likelihood is already clear for you. So we can then go for maximum likelihood estimation, right? First thing, we'll take the same example. N is equal to 10, which means you are doing a total of 10 coin tosses. What was the observation that we had in the last lecture? We said when you did 10 tosses, you got 8 heads and 2 tails. So generally when you toss a coin, you are expecting 5 heads and 5 tails. Here I am purposefully saying that in your particular experiment of 10 tosses, you got 8 heads and 2 tails. Why am I saying this? Because in likelihood, data is fixed. You are going to find out the parameter. This is the main difference. Generally, you will be finding generally parameter will be fixed and you want to see for data. Here, your data is already fixed. I'm telling you, you did the experiment, you got 8 heads and 2 tails. Why are we using this logic in machine learning? Because if you're training a machine learning model, the data for training is already given. The data is already fixed. According to the data, you want to tune the parameters of the model. This is the logic. This logic is the reason why you always use likelihood and maximum likelihood estimation in machine learning, because you want to find the best parameters of the model when the data is already given. This is the most important point. So I'm giving you the data already. I'm telling you 10 experiments, you got 8 heads and 2 tails. Now you find out the parameters. This is the task. Okay. So again, we'll find likelihood and do the same steps. Probability, we are considering it as Bernoulli, then probability of x is equal to head. What will be this probability? I am saying this is P. Then what is the probability of x is equal to tail? In Bernoulli, it will be 1 minus P. In this case, last lecture we already reached till likelihood. Likelihood will be P raised to 8, 1 minus P raised to 2. Why is this? Because you got 8 heads and 2 tails. For heads, the probability is P, and for tails, probability is 1 minus P. That is why your likelihood is P raised to 8, 1 minus P whole raised to 2, right? At this point, you have likelihood. Next step is, we already said we want to find log likelihood. If you take log likelihood, then what happens? If you take log likelihood, I'll write it as small l so that later I can simply use small l. This is my log likelihood, okay? Log of LP. What happens if I take log of this? I'm going to take log of P raised to 8 into 1 minus P raised to 2. When I take log, product will become sum. This is what we already discussed. When it is raised to 8, this will become, instead of exponentiation, it will become product. So this can be written as 8 log P plus 8 log P plus, what will this become? It will be 2 log 1 minus P. This is what you get after taking the log. You can see likelihood was this term, log likelihood is this term. Clearly, this term is way more numerically stable because here you are having product and exponentiation. It is converted to summation here. Because of that, it is numerically stable. Now you have log likelihood. What is the next step that we learned? Next step that you should do is you have to take dl by dp. You have to differentiate with respect to the parameter. So parameter theta is p here, okay? P is a parameter. So your parameter theta is p here. If you take dl by dp, you are differentiating with respect to the parameter p. Then what will this become? It will be d by dp of 8 log p plus d by dp of 2 log 1 minus p. What will be the solution here? When you differentiate 8 log p with respect to p, what will you get? You will get 8 by p, because log x when you differentiate will become 1 by x. That is why it is 1 by p. Plus, what will this become? It will become 2 by 1 minus p into, you have to take derivative of 1 minus p. So if you do d by dp of 1 minus p, it will be minus 1 because it is minus p. So this into minus 1. So instead of writing minus 1 here, I will make this sign as minus. This is what I found out when I took derivative with respect to p. I took log likelihood, then I took derivative with respect to p. What is the next step? Next step is, I want to say dl by dp is equal to, I want to equate this to 0 so as to find out the parameter theta. So theta is p here. I want to find the value of p. For that, I am going to equate it to 0 and I'll try to find out value of p. So if I equate this to 0, what happens? 8 by p is equal to 2 by 1 minus p. I am equating this to 0 and I am solving, okay? Then it will be 8 by p is equal to 2 by 1 minus p. If I solve for this, what happens? 8 minus 8p is equal to 2p. If I take that 2p to the other side, 10p is equal to 8, which will give me p is equal to 8 by 10, which is 0.8, which means the likelihood is maximized at p is equal to 0.8. Then p is equal to 0.8 is my maximum likelihood estimation. So this is the whole concept of maximum likelihood estimation. Now let us discuss. What does this mean for you? This means the data. What is the data that you had? Your data was 8 heads and 2 tails. This is the observation that you had. This data that 8 heads and 2 tails will occur when you do 10 coin tosses. This particular data, this provides the strongest support for coin toss having bias 0.8. If you are tossing with a coin which is having a bias of 0.8, which means with this particular coin you have 80% chances of head and 20% chances of tail. If you use such a biased coin, then the probability of getting 8 heads and 2 tails when you do 10 coin tosses is the maximum. So at this point you can think, okay, if you simply told me you got 8 heads and 2 tails, I would have directly told that probability of 0.8 should be that of the coin. That should be the bias. But the point is, I purposefully took an example which is easier for you to understand, so that once I complete my this MLE estimation, maximum likelihood estimation, you should be convinced that whatever I reached finally, that is actually the correct answer. You should be convinced of this. Because of that, I purposefully took one particular example, was simply by looking at this itself, you would have told, okay, the coin should have a bias of 0.8, then this particular data's probability will be maximized. I want you to understand this concept. So now you understood that if you do this MLE process, if you find the maximum likelihood estimate, then whenever you are given some particular data, you will be able to find out the parameter which will maximize the chances of occurrence of this data. This logic is the most important, the core part in understanding how to train a machine learning model, right? So a few more things here. You understood that maximum likelihood estimate is at p is equal to 0.8, which means your data's probability is maximized when your parameter p takes value 0.8. But keep in mind that do not interpret this like probability that p equal to 0.8 is the highest. That is not the logic here. Likelihood is not a probability distribution over p. So you have to understand this, that you should not interpret this like probability that 0.8 is the highest. No, that is not the logic here. The logic here is, if you use your parameter as 0.8, then the chances of this particular data being observed is the maximum. That is what maximum likelihood estimate says. Likelihood is not a probability distribution. It is not a probability distribution. In the last lecture also we clarified. So I want to clarify again that it is not a probability distribution. It just tells you the data is more likely under p equal to 0.8 than under any other value of p. This is the whole logic. Okay. So this is why you should always go for maximum likelihood estimation when you are training a machine learning model, right? So this is it about maximum likelihood estimate. Understanding this is the core part in understanding how you actually train a model, how you actually deal with data. That is why you would always see maximum likelihood estimation used in machine learning derivations.